Okay, up until this point, we've only looked at differentiating basic functions, things like x cubed, x to the 4, 2x squared, etc., etc. But unfortunately, the real life and most of maths doesn't work like this. And most functions we encounter are going to be weird. They're going to be sine, they're going to be cos, they're going to be exponential, they're going to have some division in there, or any number of things, right? So we need to know how to differentiate these as well, because they're more important than our easy ones. So we're going to start off with sine and cos. I'm going to show you how we prove the derivative of sine and cos, and then how we can use it as well. So I'm going to start off by proving the derivative of sine using the first principles formula, the idea of first principles. If you're unfamiliar with this, if you're not happy with this equation, please go and watch my last video on it, because I won't be covering this in much detail here. I'm just going to be using it. So I'm going to start off with f of x equals sine x. And I'm going to plug this into this formula and see what happens. So if f of x equals sine x, then I'm going to have the limit as h tends to 0 of f of x plus h. So x plus h is the argument of my function. So this argument changes to x plus h, and I get sine x plus h minus f of x, which is sine x, all divided by h. Now, at this point, you might look at this and go, I mean, what do I even do with this? Right? It doesn't look like there's anything I can do. Well, I'm going to start using something called the addition formula, the trig addition formula. I haven't covered these yet on this channel, but I probably will this week. If I can be bothered, I'll see. But we're going to be using these. And this addition formula here, what I'm going to be using, states that sine of a plus b is equal to sine of a cos b plus cos of a times sine b. And as you can see, I've got a little thing at the top there telling me that in order to make this the same and usable, I want to say that x is equal to a and h is equal to b. And if I pop all that together, then I get, always remembering to keep my limit in until I use it, sine of x plus h becomes sine x cos h, not cosh. If you don't know what cosh is yet, ignore I even said anything, but always looks like cosh, plus sine of h cos of x minus the sine x divided by h. Now, once again at this point, you might want to pause and think, what the bloody hell do I do here? Because it's not like in the last examples with first principles where I can start cancelling some h's and I just have something nice and easy left over. So there are two tricks that I'm going to want to employ here. And the first one is this idea of a small angle approximation. So again, I've got a video on this if you're not happy. So for now, I'm just going to state it, that sine of x is roughly equal to x, and cos of x is roughly equal to 1 minus x squared over 2. If you're looking at these saying, what on earth is going on here? Check out my video on small angle approximations. So I'm going to be using these, and I'm also going to do a kind of a horrible little trick, which is to split this up, and you'll see why. I'm going to split up this formula. So I'm going to keep my limit in, always keep the limit in, and I'm going to split it into two different fractions. The first one, I'm going to include the sine x cos h and the minus sine x. And I'm going to factor out a sine x from that. So if I factor out a sine x, I'm going to be left with cos of h minus 1 divided by h. And you'll see again in a minute why I have kept this sine x out, but you know, this is the same as having that on the numerator. And then I am going to add on to it the other part of the fraction, which is going to be sine h cos x over h. These two things are exactly the same. This red and this blue are exactly the same. I've just split this up because it's going to be easier to see what's going on. Now, I'm now going to combine these two together. What do I mean by that? Well, I'm going to apply these to my h values. So I'm going to say that sine of h, and I'm going to write this, I'm running out of space, I need a big board. Why don't you use the board in your classroom? Because I can't be bothered. Let's write it, let's do it up here, tiny little box up here, that's fine. So I'm going to say that sine of h is just h, and cos of h is 1 minus h squared over 2. So just these formula here, but applying it to h. So if I do that, then this thing here, this cos h minus 1, becomes 1 minus h squared over 2 minus 1 over h. And that becomes, well, 1 minus 1 is 0, so then I've got minus h squared over 2 over h, and minus h squared over 2 divided by h is minus h cubed over 2. And then over here, I have got sine h, which is just h, over h times cos of x. So h over h times cos of x just leaves me with cos of x. So I essentially end up with sine of x times all that nonsense, which I'm just going to rub out just to be a bit neater. So I end up with sine of x times by minus h cubed over 2 plus cos of x. And we still have the limit as h tends to 0 of all of that. And now we can apply our limit, which is to say replace any h with a 0, which means here I have 0 divided by 2, 0 times by sine x, that disappears, and I am just left with cos of x. So the derivative of sine is simply cos. Okay, following on from that proof, I have got that the derivative of sine is cos, and also, I haven't proved this, but the derivative of cos is negative sine. This thing here can be proven exactly the same way using our first principles formula, using the exact same method that I did earlier, just using addition formula for cos, and then using the same small angle approximations. I'm not going to do that here. If you would like to see me do it, mention it in the comments. I might make a quick short because it's only a very small thing. And what I wanted to mention here is I wanted to state these two and then just mention what happens when it gets weirder. What happens when I have sine of 2x, for example? What does that differentiate into? Because again, I don't want to be doing the whole first principles thing every time. I'd rather just be able to look at it and know. And luckily I can. What happens is, when I have sine or cos, I'll show you a cos in a minute, sine of anything that isn't just x, okay? I need to take the derivative of whatever is inside the argument. So whatever is inside these brackets. So differentiate 2x. And if I differentiate 2x, I just get 2. And then I'm going to take the entire function, or the key bit is the sine, and differentiate that. And we know that sine differentiates to cos, so I'm just left with cos. The argument stays the same. So if I have a number inside here, or anything else inside here, I need to differentiate the interior, bring that outside, and then just apply my rule to the rest of it. So if it was cos of 3x squared, for example, same logic. I'm going to take the argument inside, 3x squared, I'm going to differentiate it. 3x squared differentiates to 6x. And then my whole thing, particularly the cos, or cos differentiates to negative sine, so I end up with minus sine, and the argument stays the same, of 3x squared. So I end up with minus 6x sine 3x squared. Now, this process that we've just done here, applies to a lot more functions, and it's something called the chain rule that I'll be covering in 2 videos, maybe 2, maybe 3, maybe 2 videos time. But the chain rule comes up a lot, but for now we can just look at this as a nice easy way to differentiate sine and cos. As long as you remember that sine differentiates to cos and cos differentiates to negative sine, then we will be all good.